I'm Masakazu Fujio with Hitachi Japan. In this presentation, I'd like to introduce template protected authentication based on location history and B-bit MinHash. Introduction. With the progress of IoT society, our life becomes more convenient, comfortable, and higher efficient. On the other hand, the damage caused by account leakage and impersonation is also increasing. Secure and reliable identity authentication is becoming more important, but balancing safety and convenience is very difficult. In the literature, there are some studies for mobile device authentication by behavior data. They collect user behavior through IoT such as smartphone sensors and authenticate identity using the user model created. They pursue the balancing of safety and convenience. Here is an example of location history of one day in Tokyo City from morning till midnight collected by the MISRA project promoted by the University of Tokyo. Purpose of this paper is to investigate the availability of location history for template protected implicit authentication. But there are some problems when using location history for user authentication. One of the problems is the fluctuation of behavioral data, such as change of commuting and returning home time, take a detour on the way to the home, and gaps in the collected data, sampling rate of GPS data, or the operation error such as power off, forgot to bring the cell phone. Other big problem is privacy issue. Location history can contain highly privacy information, such as home places, play spots, and hospital. To handle the former problem, we propose set similarity measure, modified weighted Jaccard coefficient, MWJC in short, and propose user authentication method based on location history. To handle the second problem, we designed a method to secure the calculation of the weighted Jaccard coefficient using MinHash, TP-MWJC in short, and propose template protected authentication by using location history. Then we show that proposed MWJC achieves practical accuracy compared with the conventional location history authentication, and that TP-MWJC achieves comparable accuracy to MWJC. Our proposal 1, modified weighted Jaccard coefficient. In this slide, we will explain our proposed authentication method. The upper side in this figure shows enrollment steps. The client application needs to gather location history from each user's smartphone for about a few weeks to create an authentication template. Then the application converts discretized location and time data into protected template using MinHash and template protection technique, and then converted data to the authentication server with his ID. The lower side in this figure shows authentication steps. Similar to the enrollment process, location histories are converted into protected templates, then send them to the authentication server and calculate the similarity between templates. In this study, we used 1 day's profile for user authentication. Here's a case study of GPS history. Since the GPS and time are continuous values, the authentication template is generated by discretized location data for each time frame. For example, the time frame is discretized in 1-hour units, and the location information is discretized with 100th degree, about 900 meters. Here is an example of 1-day profile data. In this case, we have 24 set data with different cardinalities. Each set consists of latitude and longitude pairs or frequencies with 100th degree. Once the location templates are created, we can define set similarities between templates. Here we define the 4-set similarity measure we tested in this study. We adapted a normalized set similarity measure, Jaccard coefficient, to handle the data volume gap between templates. The last one is our proposed measure, modified weighted Jaccard coefficient. For the detail of formula, please refer the paper. Finally, we can calculate the similarity between templates by the sum of set similarities from each time frame. Our proposal 2. As we mentioned previously, when we use location history for user authentication, we have to keep the data secure from the risk of data leakage. Cancelable biometrics is one of the template protection scheme where an intentional and systematic distortion is applied to the biometric data such that it is difficult to recover the original biometric data from the transformed data. CB schemes should meet these 4 criterions: irreversibility, revocability, unlinkability, and performance. This slide explains the outline of the MinHash. The MinHash applies k-hash functions h sub k to a set elements S and select the smallest hash value for each hash function. Then check if the selected value is equal to that of the other set. The Jagged coefficient is estimated as b over k, where b is the number of matches. B-bit MinHash convert MinHash vector into a binary vector of length k times b by taking the least significant b-bit from each MinHash value. By increasing the number of hash functions k, we can approximate the Jagged coefficient more accurately. This figure explains the overall system architecture of DP-MWJC. The dotted line is the steps of the enrollment phase. The solid line is the steps of the authentication phase. The application converts GPS data into bit vector, big text B, using MinHash. The converted bit vector is XORed with user-specific random filter R. Then store the key R at each user's device. This slide explains that the proposed method satisfies requirements for template protection. The first requirement is irreversibility. To meet the irreversibility, we should say that independence between plain text M and ciphertext C. If we XOR a uniform random filter R of the same size to the b-bit MinHash vector M and keep the filter secret, we can derive independence of plaintext M and ciphertext C, which correspond to the irreversibility. For the detail of the derivation, please refer the paper. Other requirements are as follows. To meet unlinkability, we should say the independence between ciphertext C1 and ciphertext C2. Similarly, as the case of irreversibility, we can derive this formula by replacing plaintext M with ciphertext C1. In case of revocability, when the templates or secret key R are compromised, the system can cancel the template by issuing a new secret key R dash and regenerating the templates. Then the proposed method meets the revocability requirements. For the performance, we will explain in the experiment section. To reduce the risk of spoofing, the prevention of replay attack is also necessary. This slide shows a system overview for preventing replay attacks. Using this architecture, the template that follows over the network can always be a one-time template, preventing authentication using a badge template. Experiments. This slide summarizes the experimental setup. We used the MISRA project dataset collected by the University of Tokyo for evaluation. We extracted 200 persons that have more than 60 days record. Then we used one-day profile of the DPS data for each template. We registered the first 30 days of data for enrollment, then used the remaining 30 days for validation. At verification time, we performed a round-robin check with all the enrollment templates. Authentication accuracies are evaluated based on the similarity with the most similar template of each user. For the evaluation metrics, we used FAR, false acceptance rate, FRR, false rejection rate, and EER, equal error rate. Evaluation without template protection. The experimental results show that the EER is less than 2% and the discretization of 1,000th degree is good with all four metrics. As you can see in the lower table, in the work of the Wigton 2011, they show the misclassification rate is 2.9%, which is worse than our result. In the work of Friedman 2016, they say that FRR is 5% and FAR is 10% when using location data only, which is also worse than our results. Besides, they say that EER is 1% when they combine four behavioral data, such as text typed, application visited, website visited, which is better than our results. Multi-factor authentication is also in the scope of our implicit authentication. The improvement of the accuracy by using more rich behavioral information is our future work. Evaluation with template protection. For the b-bit MinHash parameters, the number of hash function k, the length of bit b, we used these parameters. We also evaluated standard MinHash cases. This table shows FRR values when FAR is lower than 0.001%. We can achieve an FRR of 8.2% with the degradation of 1.7% from FWJC when we use 256 hash functions and 16-bit of the hash value. In addition to that, we performed an additional experiment using standard MinHash and get better results. When we use 512 and 1024 hash functions, the FRR is better than the original MWJC. Standard MinHash can be considered as full-bit b-bit MinHash. Discussions. For the dictionary size, if we use 1024 hash functions and each user has 30 days templates, the size of the template of a person is about 123 kilobytes. The authentication time is 10 milliseconds for matching 30 templates. Note that the server only needs to match genuine templates in authentication time because the target person is known at the authentication time by smartphone ID. This paper proposed a template-protected user authentication with the location histories collected through a personal mobile device. We first proposed a new set similarity measure, modified weighted Jaccard coefficient. Then we designed a method to secure the calculation of the weighted Jaccard coefficient using MinHash and proposed template protection authentication architecture. Experimental result shows that our proposed method outperforms the conventional location history authentication without template protection, while ensuring the irreversibility, revocability, and unlinkability required for template-protected technique. Future work. When using location history only, it is impossible to tell the person is the same one or not if they are going where they usually don't go. The system needs to use other information such as touch screen operation, application visited, website visited. The improvement of the accuracy by using more rich behavioral information is our future work. And in this study, we used a one-day profile of user mobility. Authentication with less data is desired for timely fraud detection. The evaluation and improvement of the accuracy with less data is our future work. Thank you for listening.